All right, guys, let's keep going through the TCA cycle here. So we've up to the point where we've made citrate, right? We've seen how we can use the characteristics of that acetyl-CoA, that thioester bond, to create that carbon-carbon bond that takes oxaloacetate um, and that acetate group and creates citrate, and then or citryl-CoA, which then gets hydrolyzed to form citrate, that nice tricarboxylic acid that lets us now sort of commit into the TCA cycle, right? So I'll just draw that out again here for you. Right? Okay, so it's citrate. All right, the next step of this reaction, if you remember last time we ended the talk, is we need to do something to set up the removal of those two CO2, those two carboxylate groups, which we're going to get rid of as CO2, right? And the key to this is to exploit that alcohol group and move it and turn it into a carbonyl. And that's what the next reaction does for us. It basically moves that alcohol group over one carbon. So essentially what we're going to run is a sequential dehydration rehydration reaction, right? So we're going to basically run an elimination of water to create in the active site of this enzyme this molecule, which is also known as cis-aconitate. Right, so that's our dehydration step. And then we're just going to run a rehydration. We're going to basically put the water back on, and essentially by rehydrating across that carbon-carbon double bond and moving the alcohol group over here, right? We pulled the water off to create the cis-aconitate, the carbon-carbon double bond, and now we're just basically going to put the hydroxyl back on the other side, on the other carbon, right? Now we're going to put water back in to create our tricarboxylic acid with the hydroxyl moved over one here, deisocitrate. Okay, now just to keep you referenced, remember again, these were our carbons that came in right here from acetate, from the acetyl-CoA. All right, the enzyme that runs this reaction is known as aconitase. Right, free energy of this sequential dehydration rehydration reaction is super not favorable, right? The standard state free energy change for this reaction is plus 63 kilojoules per mole. That should make you sit up and go, whoa, that's like I think that's the worst one we've seen so far. That is the most unfavorable reaction in the forward direction, the way we were thinking about these pathways that we've seen, right? I mean, the aldolase reaction wasn't great, but this is worse, right? So that immediately tells you what you could expect in an actively respiring tissue running this cycle about the concentration of deisocitrate. Oh boy, does this have to be yanked super low to get this reaction to go in the forward direction. Again, I haven't been able to locate the cellular conditions, but it's going to be less than 0, but maybe barely, right? It's going to be favorable in the forward direction. It has to be thermodynamically, right? But it's not going to be super favorable, and you're going to have to pull it by draining the deisocitrate pool, which is exactly what happens when the TCA cycle is running actively. Okay, now there are a couple of things worth thinking about. One you may already be looking at and going, wait, what? We'll come back to it in a second. It has everything to do with the stereochemistry of that central carbon. I'm going to think about it for a second. But while you're thinking about it, let's talk about this enzyme aconitase. Now, to get this reaction to go, aconitase uses a cofactor we haven't talked about yet. I think I hinted that these were coming, but we haven't actually seen one of them yet. This is going to be our first example. Aconitase is an iron sulfur cluster enzyme. Now, we are going to see mostly the use of iron sulfur clusters later when we talk about how we really extract as much energy as possible from these high potential electrons. This enzyme uses the same sort of metal sulfur or cofactor, but it's using it to activate water, right? So here's aconitase. Is the enzyme. There's the active site. Right down the active site is this cubic arrangement of 4 iron atoms and 4 inorganic sulfurs with a couple of cysteine residues providing a couple of other coordination positions to, 3 cysteines providing additional sulfurs to coordinate some of the irons in this sort of iron sulfur cubic arrangement. One of the irons at the very apex of this arrangement, right, that has one of those coordination positions open, is where all the business of this molecule happens. You'll notice here, there is an activated water molecule. It's a hydroxyl group, basically. It's had one of its protons stripped off, right? These iron atoms are really good at doing this, right? And at the same time, in some of the other coordination positions for this iron, is there's that central carbon of citrate with that central carboxylate group and that hydroxyl group. You'll notice they're coordinated to that central iron. And essentially what this enzyme is going to do is pop that hydroxyl off. The molecule will then form that carbon-carbon double bond, and then it will stick the hydroxyl then back on the other carbon, right? That's more or less what it's going to do. It's going to pull the one alcohol group off and then use that activated water to put the alcohol group on the other carbon, right? Okay, which is pretty neat. Right, but let's go back to that question I left you with. We were looking at this reaction just a moment ago, which was, how is that possible? You'll notice something. 2 things, potentially. One, I'm claiming that I can, this molecule, I know where the carbon identity is. I still know where my carbons are that came in from acetate, number 1. Number 2, claiming this is diisocitrate, which means it's chiral, which makes some sense. If you look at this molecule now, you'll notice that this carbon, central carbon, is now chiral. Wasn't before. Look here, right? You remember your basic organic chemistry. You'll recognize that that central carbon is not chiral, right? There's this sort of acetate-like, 2-carbon methylene carboxylate group. Those are exactly the same. But I'm claiming that aconitase can stereospecifically and with precision only move the alcohol group over to 1 carbon in to the left, as I've written it here, instead of to the right. How could it possibly do that? All right, and when it does it, it only ever generates the D isomer and not the L. Okay, the answer to that has to do with something known as prochirality. Turns out, aconitase, it's possible to do something that seems like stereochemical magic with a otherwise symmetric molecule to recognize nascent chirality in a part of the molecule if you have an asymmetric surface to work with, and that's what the enzyme provides. All right, so here is our acetyl, there's our carboxyl group, our carboxylate group coming in on acetyl-CoA to make oxaloacetate, and here, of course, is our citrate, right? And there are 2 ways in principle, because the 2 halves of the molecule are symmetric, right? That methylene carboxylate group are the same. We could, in principle, arrange that central tetrahedral carbon in one of 2 ways, with either that carboxylate that came in from acetyl-CoA up, right? Or with the other carboxylate that was already there, right, in oxaloacetate, it up. But because that carbon's tetrahedral, recognize something here, right? Even though this group and this group, they're exactly the same, the positioning of the other two groups on that central carbon aren't the same in an asymmetric active site. In one case, with the carboxylate group from the acetate up, right? The central carboxylate group is in, say, this hole. The alcohol group is in this hole. But let's say I build that active site in such a way that the positions of interacting bits in the active site are only compatible with a carboxylate group here and an alcohol group here. They won't accept the opposite of the carboxylate or the alcohol here, right? In that case, what that means is this binding configuration is disallowed, right, by the construction of the active site enzyme, which means even though this carbon is not formally chiral, it contains nascent chirality, it has prochirality that's built into the asymmetric arrangement of these three groups, right, relative to an asymmetric surface, right? So the enzyme actually can recognize that feature of this molecule, even though that central carbon is not formally it's not formally chiral. It can recognize that arrangement and therefore only allow the reaction to happen in a particular way, and always then put the alcohol group, when a aconitase puts that alcohol group back on one face of the molecule, one carbon in one face, right? Okay, so that's how the enzyme manages to retain carbon identity, even though that central carbon is not formally chiral. All right, so let's go on to the next reaction. So I wrote this down as reactions 3 and 4. People once upon a time thought that cis aconitate was a bona fide intermediate of the cycle. Turns out it never actually leaves the active site of the enzyme. Citrate forms cis aconitate in the active site, and you can mess with things and isolate cis aconitate, but it doesn't ever really leave. So in the sort of standard parlance of reactions, these were thought as two separate reactions. They're really not. I still write it as reaction 3 and 4. So that gets us 2 for 1, right? So we're up to reaction 5 now. All right, so reaction 5. Okay, so we created, using the magic of prochirality in the active site of aconitase, we've now created this stereoisometrically or enantiomerically pure version of D-isocitrate, right? Right? And remember, what we need to do now is get rid of a carboxylate group, right? And these, again, and these are the guys we're going to go after, right? And this one here, that's the easiest one. We're going after that one first because we can create a beta keto acid quite easily at that position if we turn that alcohol group into a carbonyl. And that's what reaction 5 of the pathway does. We're going to take some NAD+, right? We're going to turn that guy into a carbonyl group. And in the course of doing that, the molecule will decarboxylate. I'll show you that in a second. And the product of this reaction is then this dicarboxylic, 5-carbon dicarboxylic acid, alpha ketoglutarate. And again, keep your eye on the birdie, right? There's our carbons. All right, we can still keep track of them thanks to the stereospecificity of cis aconitate and the magic of prochirality. Of course, creates some NADH. The enzyme that runs this reaction is known as isocitrate dehydrogenase. Could have guessed that one probably, right? The standard state free energy change for this reaction is quite favorable, minus 20.9 kilojoules per mole. And you can sort of see why, right? Just like we saw with the pyruvate dehydrogenase reaction, we're powering an oxidative decarboxylation reaction, right? We're going to drive that CO2 group off. Should have written that over here, huh? We're going to drive that CO2 group off here, right? It's a great leaving group. Essentially, it's an irreversible reaction. And by coupling that elimination of CO2 to this reduction of NADH, we have a super favorable reaction, right? The next step of the cycle. Now, this looks sort of straightforward, or it is really straightforward, but there's an additional step in here that happens. It's sort of a two-step process of the formation of the ketone followed by the decarboxylation reaction. All happens in the active site of the enzyme. So essentially what really happens is in the first step of the reaction, the enzyme takes NAD plus to make NADH, right? To form our beta keto acid that we've been talking about. Right? This is, of course, oxalosuccinate. Right? And again, this molecule doesn't really exist outside the active site. It's unstable. It's bound in the active site of the enzyme. Beta keto acids are intrinsically unstable, but if you can do something to give them an extra little kick, like a little base catalysis or a little acid catalysis, you can get this guy right here, 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 provide a proton, reverse this guy. Oh, geez, stop it. So a little acid-base catalysis can dramatically help stimulate decarboxylation of that beta keto acid to give us alpha ketoglutarate, right? Okay, so it's basically fairly straightforward reaction. Once we've got the ketone, all basically downhill, a little acid assist in the active site of the enzyme. And in addition to eliminating our first CO2 group, we've also created our first set of high potential electrons from the main body of the cycle, right? Second equivalent, right? Because we have one at pyruvate dehydrogenase, and now we've got one here at isocitrate dehydrogenase. All right, reaction 6. Okay, so once we formed alpha ketoglutarate, right? Remember, the name of the game here was again to create a way to decarboxylate this, drive off some of these CO2 groups. All right. So first we created that beta keto acid, but because of where aconitase put that alcohol group, we got a second shot, right? By putting the alcohol group over here at sort of that second carbon, we got the free-fer of eliminating the CO2 group here from the previous step, right? When we had deisocitrate. Now, what we've got is an alpha keto acid. Look here, right? Here, it's the next CO2 group we're going to get, and it's alpha. It's one carbon over from that ketone. So in principle, we know how to do that because we've seen 2 examples of it. You've seen 2 examples of decarboxylation of an alpha keto acid. And you can already begin to guess, I bet you, what the cofactor is going to be involved, that's going to be involved in doing this, right? All right, I'll give you a little more of a hint of what's going to go on. Because we're about to create another thioester. This enzyme is going to take some reduced CoA, right? Some NAD+, right? We're going to run another oxidative decarboxylation reaction. We're going to create a new thioester off that carbonyl, that ketone group. We're now going to, when we kick off the CO2 group, we're going to simultaneously turn that into a thioester. right? To create, let me just write this out fully. This again was alpha ketoglutarate, right? To create succinyl-CoA. Plus some NADH, right? And some CO2, right? Because we've kicked that carboxylate group off the alpha keto acid and released it as essentially as gaseous CO2, right? The enzyme that runs this reaction is known as alpha ketoglutarate dehydrogenase, right? And the free energy for this reaction, as we have seen with the previous couple of reaction, the previous reaction, because we're running another oxidative decarboxylation. This is powered in a big way by that reduction of NADH and release of that gaseous CO2 is quite favorable. Standard state free energy change for this reaction is in the range of minus 33 kilojoules per mole. Again, I don't know the standard cellular condition free energy change, but it's going to be standard state free energy change that favorable. It's going to be quite favorable. Same up here. I didn't know this one either, I have to admit. But again, this one's also going to be the isocitrate dehydrogenase reaction is going to be quite favorable. All right, so look at that reaction again. Alpha keto acid. We're going to decarboxylate it. We're going to use some NAD to run this oxidative decarboxylation. How might you get that to go? Does that look familiar? It should look really familiar based on the previous lecture, our discussions of the pyruvate dehydrogenase. Remember that reaction? We had an alpha keto acid in pyruvate. We ran an oxidative decarboxylation and we ended up with a thioester. It's the same basic reaction. In fact, it's more than the same basic reaction. It's run in exactly the same way. Alpha ketoglutarate dehydrogenase is not a single enzyme. It's a complex, just like the pyruvate dehydrogenase complex. This enzyme, or this enzyme complex, also has an E1, an E2, and E3. And I bet you guys can already start to guess what the cofactors involved in this reactions are going to be. We're going to have thymine pyrophosphate, it's a cofactor for the E1. The E2 is going to need lipoamide and CoA, produce CoA. And the E3 is going to require FAD and NAD+, right? So the point here is that the alpha ketoglutarate dehydrogenase complex is a direct analog, both in the terms of the enzymology, the chemistry, the structure of the complex. It's built in basically exactly the same way with that outer shell of E1s, that secondary shell of E3s, and that inner transacetylase shell of E2s. The E2s in alpha ketoglutarate dehydrogenase have the same little swing arms. So we got the same little robotic factory doing the same sequential reaction that we talked about in the pyruvate dehydrogenase reaction. The main difference between the alpha ketoglutarate dehydrogenase complex and the PDH complex is that the alpha ketoglutarate dehydrogenase complex is not regulated in the way the PDH complex is. So all the extra elaborations of regulatory subunits and phosphorylation stuff and whatever that controls the PDH complex doesn't exist, the alpha ketoglutarate dehydrogenase complex. But the core nature of how this enzyme complex works and the chemistry it runs is the direct, exact analog of what we saw with pyruvate dehydrogenase. It's just we've got a slightly bigger molecule that we're creating a thioester with, but otherwise it's the same. Okay, that gets us through phase 2. Next time, we'll talk about how we take succinyl-CoA and turn it back into oxaloacetate while squeezing out some more high potential electrons and getting the one substrate level phosphorylation to create ATP that the TCA cycle creates.